I'm Mercurides, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 18. We're given a triangle of numbers 15 tall and 15 wide. Starting at the top and moving only downward, find the path which produces the maximum sum. As the problem description states, there are a total of 16,384 paths through this triangle. That's because for each row from the 1st to the 14th, we have a decision to make. We can go down and to the left, or we can go down and to the right. That's two choices, and we make that decision 14 times, for a total of 2 to the power 14 paths, or 16,384. Let's start by writing a brute force solution to this problem. We'll work in C# today. Like Java, C# source files generally expose one public class which contains the code for that file. We'll define our triangular grid as a list of integer lists in row major order. Our main algorithm will be recursive, so we'll end up trying every single path through the grid. Our recursive function takes the current row and column index and returns the maximum sum starting at the given position. When the row number is greater than or equal to the height of the grid, we've hit our base case and can simply return 0. Otherwise, we take the current grid position and add it to the maximum of the left and the right paths, calling our current function recursively to compute them. Finally, our main function simply invokes the algorithm, starting at position 0, 0, and prints the result to the screen. This function works instantaneously and already gives us an answer. But as the problem statement hinted, this is an exponential time algorithm and won't scale up very neatly if we found ourselves with a larger data set. The problem, as we've seen before, is that we're repeating a lot of recursive calls. Once we hit, say, the 47 on row 3, it doesn't matter how we hit it, because the rest of the recursive computation will be the same from this point on. And we'll definitely hit it 2 different times, once from the 95 and once from the 64. The next row is even worse. The 2 middle positions on row 4 are going to get hit 3 times each. That means we'll run those recursive calculations 2 more times than necessary, and it only gets worse with each subsequent row. We could memoize intermediate results. C# doesn't have a built-in memoization library, but we could pretty easily implement the caching dictionary ourselves. However, we can actually do even better. Each row only depends on the previous row, so let's modify our array in place and use it as our cache. At each loop iteration, we'll update the position in the array, live, to be equal to the maximum of the position to the upper left and the one to the upper right. At the end, the bottom row will have accumulated the maximum path that reaches that particular ending point. So we simply have to take the maximum of the bottom row and print it out. As an aside, the max method we're calling here isn't actually defined on arrays or any of its implemented interfaces. Max is an extension method, which means it's declared separately as a standalone function, and it only looks like a method call because C# provides syntax sugar to make it so. If the system didn't provide us with this max method, we could have written it ourselves and still gotten the nice postfix .method syntax. In our specific case, the max extension method was provided by the LINK technology, which was added to the .NET framework in version 3.5. LINK stands for Language Integrated Query and provides a uniform syntax and method collection for operating on arrays, other .NET collections, XML documents, SQL databases, and any other data source that happens to be LINK enabled. In our case, we're only utilizing the bare minimum of what LINK is capable of, but it's good enough for now. This program is nice, but I still have some notes. We count from the top to the bottom, meaning each cell in the bottom row contains the maximum sum out of the paths that end at that position specifically. But that still requires a post-processing step to find the maximum of those values. If we instead run our computation in reverse, starting at the bottom and accumulating up to the top, then the maximum from any position in the bottom row to the single goal position at the top will be stored in cell 0, 0. This eliminates our post-processing step of finding a row maximum. On top of that, since our rows are drawing information from the larger rows rather than smaller ones, this disposes of those pesky bounds checks, and we can simply access our array positions directly inside of our loop. We've got our algorithm, let's talk about our language. This week, we're going to be solving Project Euler in a Makefile. Specifically, we'll be using GNU Make. Most people know of Make as an intermediate build automation tool which helps to perform only the parts of the build process we need based on which files have changed since the last run of our Makefile. The steps of the build process are usually written in terms of shell commands, using whatever shell is available on your system. But we're doing a programming language challenge. It would be cheating if our so-called Makefile solution simply delegated all of its work out to an external shell, so the Makefile we write today will only have one rule, all, and that rule will have no commands or dependency. We're not going to call out to a shell. Everything we'll do today is entirely within the confines of the Makefile syntax. Beyond the dependency management and shell invocation capabilities, Make also supports assignment of variables and string interpolation. We'll be limiting ourselves to this expansion-oriented side of Make today, so this challenge is centered around string substitution. We define top-level variables in one of 2 ways. The first and simplest is with colon equals. When we define a variable with colon equals, it creates a simply expanded variable. That is, the right-hand side of the assignment operator is scanned immediately for any instances of string interpolation. Those instances are resolved at definition time, and the resulting variable will not be expanded again when it's used somewhere else in your code. These behave most like variables in other programming languages. You set their value once to a constant string, and that's the value from then on. The second definition mechanism is with a single equal sign. A single equal sign constitutes a recursively expanded variable. In this case, the right-hand side of the assignment operator is not scanned for interpolation, and its entire string representation, including possible interpolations, is stored in the variable. When we later use this variable in another context, its value is then scanned for interpolations, and the result of that operation at use time is the real value of our variable. This means that the value of a recursively expanded variable can change depending on when and where it's substituted. In this way, recursively expanded variables behave much more like zero-argument functions in other programming languages. In terms of using variables, we substitute a variable into whatever context we wish with a $sign followed by parentheses. Inside the parentheses, we place the name of the variable. We can substitute variables into the values of other variables, into shell commands, into a rules dependency list, or really anywhere that's expecting a string. Note that the only data type in Make is a string, so anytime we see a word that isn't an interpolation, we can assume it's being treated as a literal string, similar to the way shell scripts work. Make also comes with a meager set of built-in functions that we can call inside of our program. We'll discuss the ones we need today in turn. Info is a simple function of one argument. It prints its argument to standard output and returns the empty string. This is how we'll print the final result of our program. If is a function of 2 or 3 arguments, and it works like the if statements in most languages. If the first argument, which is the condition, is truthy, then the second argument is expanded and returned. Otherwise, the third argument is expanded and returned instead. If there is no third argument, then it defaults to the empty string. Naturally, if and the other conditional functions have non-strict arguments, which means if only evaluates the branch it intends to take, rather than evaluating all of its arguments up front. One might reasonably ask at this point what truthy means in Make. After the if function evaluates its condition part, it removes all leading and trailing whitespace and then considers whether the resulting string is the empty string or not. If it is, then it's considered falsy. If not, then it's considered truthy. So in effect, strings which are either empty or consist only of whitespace are considered falsy, and all others are considered truthy. The next few functions perform specific operations on strings, and it'll become clear why we need them in a moment. Subst performs string substitution. It takes 3 arguments, the needle, the replacement text, and the haystack, and replaces every instance of the needle in the haystack with the replacement. Note that this is not a regular expression substitution, it only matches literal strings. Word takes an index and a string. The index is interpreted as a base 10 number and is used to select the nth word from the string, where the words in your string are defined to be delimited by 1 or more whitespace characters. So, for instance, yes, no, and 40 is a number hyphenated are all individual words. But the string 40 is a number with spaces in between consists of 4 words since they're separated by spaces. Word is 1-based, so the first word of a string is indexed by the number 1. If the string has fewer words than the given index, then word happily returns the empty string. The words function also operates on words. In this case, the function takes a single string argument and returns the number of words in the string with the result written in base 10. The last few functions are oriented around control flow. For each takes 3 arguments and works like a for each loop in many programming languages. The first argument is the name of our local looping variable. The second is our list of words. Similar to Bash, loops in Make iterate over the whitespace delimited words in a string. For each word in our string, the variable is locally bound to that word, and then the third argument, our textual string, is expanded with that local binding in place. The results of the evaluation are concatenated, with whitespace separating the individual values, and are used as the final result of the for each call. The binding to the variable is local and doesn't have any long-term effects on a global variable of the same name. Eval does exactly what it sounds like. It takes a string as argument and evaluates that string as Makefile syntax. The result of eval is always the empty string. That is, the evaluation is done for side effects. This can be used to declare new top-level variables or define new syntax, similar to a macro. Finally, there's call. So far, we've only discussed built-in functions, but it's possible to write global variables that behave like functions. Everything in Make is a string. There's no number type, and likewise there's no function type. But call can treat a string like a function. Specifically, call takes a variable name as its first argument, followed by 0 or more parameters. The variable with the given name is expanded, with the local variables $1, $2, $3, and so on bound to the parameter values given. So if we want to write a function that takes parameters, we simply declare a variable with recursive expansion that uses those numerical variables, and then we invoke it with call. We'll see a concrete example of this in a moment, but first, we need to discuss numbers. So far, only 2 of the operations we've discussed have mentioned numbers. Word can select a position in the string based on a numerical index, and words returns the number of words in a string, again as a base 10 number. For our intended solution, we need to be able to add non-negative integers, compare them, and take the maximum of two non-negative integers. But nothing we've discussed so far directly allows us to perform integer arithmetic. That's because, as I mentioned before, the only data type in the make language is a string. The fact that a few of the built-in functions happen to recognize certain strings as integers is incidental, but at no point are those variables actually storing numbers. So we're going to have to get a bit creative. We actually have all the tools we need to perform these three operations, if we simply encode our numbers correctly. Several of these built-in make functions operate on individual words of a string. That is, they implicitly split the string at whitespace. So here's our definition of a non-negative integer. We're going to write integers in unary, so a number n will be represented as n instances of the letter x separated by spaces. For example, the number 0 will be represented by the empty string. The number 1 will be represented by a single instance of the letter x. The number 2 will be represented as x space x, 3 as x space x, and so on. Note that in our unary representation, it's the number of words that determine the numerical value. So, for instance, the string x space x would also represent the number 2, though we wouldn't choose to write it that way if we had the choice. Likewise, a string of spaces and nothing else will represent the number 0, just like the empty string. Some of our operations might produce values like this, which are not normalized into the prettiest representation, but are still perfectly valid. Let's discuss how to convert between this unary numerical representation and the usual base 10 representation. First, the easy direction. If we have a number written in our unary sequence of x's representation, we can convert it to decimal simply with the words function. Going in the opposite direction is a bit tricky, and we're going to do it recursively. We'll write two functions, fromNum and its helper which begins with an underscore. FromNum takes a number in base 10 and expands to that string in our unary representation. The helper function will take the target number in base 10 and an accumulator argument. The accumulator argument will build up the result, which will eventually be returned from our helper. Let's design this from a top-down perspective. We start with the public fromNum function. This function needs to do two things. It needs to handle the corner case of 0, and it needs to invoke our helper function. First, we want to check whether the empty string consists only of the digit 0. If so, our result should be the empty string representing the numerical value 0 in unary. To do this, we'll perform a string substitution. Take the input string and replace all of the zeros with the empty string, effectively removing all zeros from the input. Now this resulting string is the conditional argument to an if branching call. Remember that the if function considers its condition false if it consists of only whitespace and true otherwise. If our string is just zeros, then the substitution will wipe out all of the zeros and the condition will be false. If our string consists of any non-zero digit, even if some of the other digits happen to be 0, then our substitution will fail to wipe out the whole string and our condition will be true. In the false case, we simply return the empty string, so we can leave the last argument blank. In the true case, we call our helper function, fromNum with an underscore at the beginning, passing along our original input number, and starting our accumulator argument as the empty string. Now let's talk about our recursive helper function. This function is never going to change its first argument. The input number will always be the same even after making recursive calls. Instead, we're going to change the second argument in the recursive call and stop when the second argument represents the number indicated by the first. So the first thing we need to do is check whether we're already in our base case. We want to know if the base 10 number given by the first argument and the unary number given by the second are the same. Strictly speaking, we can loosen this constraint a bit. This is a private helper function, and we know the second argument starts out at the empty string, representing the number 0. And our recursive step will effectively add 1 to the number. So we can assume the second number is always less than or equal to the first. All of this is to say that we can instead check whether the second number is greater than or equal to the first to determine if we're in our base case. And believe it or not, we have a built-in function that can do exactly that. It's called word. Recall that the word function takes a number in base 10 and a string, and returns the nth word of the string, where n is the base 10 number. In case the index is out of bounds, word returns the empty string. In our case, we pass the target number in base 10 as the index, and we pass the accumulator in unary as the string. If the accumulator is greater than or equal to the target number, then the one-indexed word function will return the letter x, since it found a non-empty word at the position indicated in base 10. And the letter x is truthy when used in an if statement because it's not whitespace. If the accumulator is strictly less than the target number, then the index will be out of bounds, the word function will default to returning the empty string, and the if statement will find its condition to be falsy. So we do our check. If it's true, we're done and we return the accumulator. If it's false, we prepend a single x followed by a space to the accumulator, and make our recursive call. And now we have a reliable way to convert from base 10 numbers to our unary representation and vice versa. Next, recall that we had 3 operations we needed to be able to perform on this representation of integers: addition, comparison, and maximum. We need to figure out how to do each of those. Addition is quite straightforward. If we have 2 integers represented in unary, their sum is represented as the concatenation of the 2 integers, with a space in the middle. Take a moment to convince yourself of that. Remember that in this representation, the number of whitespace delimited words determines the numerical value of our string. If the left-hand side has n words, and the right-hand side has k words, then concatenating the 2 with a space in the middle will result in a string of n plus k words. We've actually already seen how to do integer comparison in Make. We did it in our fromNum helper. To figure out whether a is less than or equal to b, take a in base 10 and b in unary, and call the word function with those 2 arguments. If a is less than or equal to b, then the index is in bounds, and the word function will return the string x, which is truthy. If a is greater than b, then the index is out of bounds, so the word function will return the empty string, which is falsy. Remember that we have bidirectional conversion functions between base 10 and unary now. So if our numbers aren't in the required formats, we can always adjust by calling fromNum or toNum as needed first. Once we have a comparison operator, writing a maximum function is relatively simple. Let's assume for the moment that our 2 input arguments are both in unary. To start, we check whether our first argument is less than or equal to the second, using our word trick from earlier. If so, return the second argument, else return the first. And these are our basic operations. Let's talk about how we're actually going to write this algorithm. We'll treat our input triangle as a 2-dimensional grid, similar to our approach in C#. In this case, however, we'll pad the first 14 rows with zeros to make each row have the same length. This doesn't change the numerical answer, but it does make bounds checking slightly more straightforward. In terms of actually storing our grid, we'll separate rows with spaces and columns with semicolons. Recall that our C# program started at the bottom row. Then, for each row above the current one, we joined the current data with the new row by taking each cell and adding the maximum of the 2 places we could have come from. We're going to do something similar here, except that we won't modify the array in place. Instead, we'll have a second array variable called collection. Collection is going to store our current row in a bit of an odd format. Each cell will be represented in unary, but with semicolons instead of spaces, and the cells will be separated by spaces. It might seem odd that we're constantly changing our delimiters here, but this format gets us the best of both worlds. Since cells are separated by spaces, we can easily use the built-in word and for each functions to iterate over them. And since our numbers are already in mostly unary, we can perform one simple substitution to get rid of the semicolons, and now we have our numbers in the format we need for integer addition. The bulk of our calculation will take place in a function called recurse. This is where we actually calculate our sums. Recurse doesn't return a value, but it'll have the side effect of setting our collection variable to its final value, which contains the correct answer in the first cell. Let's get started. First, we store our data. The data variable contains our triangle and will never be modified. Next, we'll write a helper function to get a particular cell from the data grid. The get function takes 2 arguments, y and x, both in base 10. It returns the numerical value, again in base 10, at the given y and x coordinates in our grid. All of our indexing functions in Make are 1-based, so for consistency, we'll write our functions in the same way. Our rows are separated by spaces, so we start by calling word to get the given 1 indexed row. Now we have a bunch of numbers separated by semicolons. In order to be able to select one of these numbers, we need to turn those semicolons into spaces with the subst function. Once we've done that, we simply call word one more time to get our result. There's a minor improvement we can make to get. Make handles this function fine, but to a human reader at a glance, it looks like we're replacing semicolons with nothing. The space isn't readily apparent to the human eye. To make this code a bit more readable, we define a variable called sp whose value is a single space. Due to Make's tokenization rules, we can't use a traditional equal sign or colon equals expansion to do this, as the space will just get stripped. So instead we use define. Define works just like the equal sign, except it can be used for multi-line strings and exotic strings, like our single space one here. This isn't strictly necessary, but it's easier on the eyes than having blank spaces as arguments everywhere. Next, we'll have several helper functions. Most of these are either functions we've already written, or minor variations thereof. So we'll go quickly. Underscore add is a function that takes 2 numbers in unary and returns their sum, also in unary. As we discussed, this is simply string concatenation. Our main add function, on the other hand, takes 2 numbers in base 10 and returns the sum in base 10. This is still just string concatenation, albeit with a few calls to fromNum and toNum mixed in for marshalling purposes. Note that because of the delayed nature of recursively expanded variables, it doesn't matter that the fromNum and toNum functions don't yet exist. As long as we define those functions before calling add, the latter will be able to run normally. Next, we write a max function. This function takes both of its arguments in unary and returns the maximum, also in unary. We've seen this before, so I shan't dwell on it. My choice of which arguments are unary and which are base 10 may seem arbitrary right now, but my goal is to minimize the number of times we have to explicitly convert between numerical representations in our main recurse function that we're going to write in a moment. Finally, we have our toNum and fromNum functions. These are identical to the ones we wrote a few minutes ago. Next, we define rows and columns. We're going to iterate from row 14, which is one away from the bottom, up to row 1 inclusive. We could define a Python-style range function that works recursively, similar to fromNum, but since there's only 14 values in our range, it's easier to just list them out. We'll use this rows variable as a list argument to for each in a moment. Likewise, in each row, we'll iterate over the columns in forward order, so calls starts at 1 and goes up to 14, inclusive. Now for collection. Collection is our accumulated array, and we want its initial value to be the bottom row of data. However, we want it to be stored in our unary with semicolons format we discussed before. First, get the bottom row of data. That is, get the nth word where n is equal to the number of words in data. Then, replace all the semicolons with spaces. At this point, we have the bottom row in base 10 with spaces separating the individual cells. This is a space-delimited list of words, so we can iterate over it using for each. For each value, we convert it to unary and then replace the spaces with semicolons. Remember that the for each construct automatically separates its results with spaces, so in the end, we have a space-delimited list of semicolon-delimited unary numbers. Now for the complicated part. Recurse is a zero-argument recursively expanded variable, which, when expanded, will perform our entire computation. I'm going to write this code with extra new lines. The Makefile syntax won't actually let us do this in the end, so we'll have to strip the new lines before we run it, but it'll make it marginally more readable for now. For each row, let y be the row index. Now what we want to do here is build a new value for the collection variable. We'll use its existing value, accumulating some new cells from data, and produce a new value for it. To produce the new value, we iterate over columns. For each column, let x be the column index. At this point, we have the indices x and y in base 10. What we want to do is get the values from our previous iteration, take their maximum, and add the value of data at x, y. We have a helper function to get a value from data, so call it. We're going to want to add numbers, so convert this value to unary. Next, we want to get two values from our collection array, the value at x and the value at x plus 1. Get those values directly with word, then replace the semicolons with spaces so we can do our usual addition function. Now we have two numbers in unary. Call max to get the larger of the two, and add that to the value we just got from data. Finally, since we'll be storing this back in collection, convert the spaces back into semicolons. After the for each loop for x runs, the value we'll have is a space-separated list of semicolon-delimited unary values representing the cells of our array. That is, the value we'll have is exactly in the format we want our collection variable to be in. This is where eval comes in. To set the value of the global variable, we'll eval a code snippet that assigns a value to the collection variable. And that's our recurse variable. We call it immediately. We could use the built-in call function here, but we don't have to. Since our so-called function doesn't take any arguments, calling the function is really the same as expanding it as a variable. After calling recurse, the collection variable contains the accumulated row of data. The first cell is our answer, and the remaining 14 are frankly garbage, since they include results that involve iterating over illegal paths that include our padded zeros. Get the first word from collection, replace semicolons with spaces, convert it to base 10, and then call info to print it out. Finally, just so Make doesn't complain about unknown jobs, we define the rule all to have no further dependencies and no actions. All of our work is done at the top level when the Makefile first loads. And that's our program. Once we strip the extra new lines, we have a working solution that calculates the maximum path through our triangular grid. And this solves Project Euler problem number 18 in GNU Make. Tune in next time when we solve Project Euler problem number 19 in QBasic.